In this video, we'll be going over the Hubble's law. So we'll start by showing a graph that shows the relation between what the Hubble's law is. We'll talk about the actual Hubble's law formula, and that's just it, and the Hubble's constant. So let's start by looking at this graph. So Edwin Hubble observed that there's a relationship between how fast an object is moving and how far away it is from us. And he put these observations on a graph where this side we have velocity in kilometers and this side we have distance in parsecs. So from here you can see, and he saw as well obviously, that the relationship was linear. So we can put this into a linear formula. So let's write some notes. So Edwin Hubble observed that the further an object was, the faster it receded from the Earth. And our second point is the relation is linear. This brings us to our Hubble's law, which says the velocity of a galaxy or any object is equal to the Hubble's constant times the distance it is from us. V is in kilometers per second, and the D is in megaparsecs. So the velocity of the moving object is in kilometers per second, and the distance of the object is in megaparsecs. And this will let the formula work. If you use meters per second or parsecs, the formula won't work as you want it to. We have to be very mindful of this because most of the measurements that we take are in meters or in parsecs. So this is a little tricky sometimes. Now, looking at this graph, let's try to find what the Hubble's constant is, or h naught. This is basically the slope that we're getting, where we have y equals mx. That's kind of parallel to what we have here. We have a linear line that's v equals h naught times d. Looking at this graph, let's try to find the slope. So we can see rise over run. So the rise is 500 kilometers from this point to this, and the run is 10 to the power 6 parsecs, which is 1 megaparsecs, right? 1 million parsecs. And with that, we get our slope of 500 kilometers per second over megaparsecs. This is wrong, by the way. This is because when Edwin Hubble took his observations, the instruments he used were very inaccurate. So today, using his methods, we found out that the actual Hubble's constant should be 70 kilometers per second megaparsecs. This is much more accurate to the universe we observe today. But even though the constant that Hubble actually found was not correct, we still call this Hubble's constant because we're still using his laws and ideas. Now let's go try some example problems. This is from the 2017 Canadian Astronomy Olympiad. A radial source in a nucleus of an active galaxy has an angular dimension of 0.001 arcseconds and a redshift of 0.5. Estimate the linear dimensions of this source in parsecs. So what this problem is asking us is that we have an observer over here. That's our observer. And it's looking at a galaxy over here. The linear dimensions means that we have to figure out how far it is. So this is something we need to find out. And we need to figure out the diameter. So there's two things that we need to give as our answers. What are we given? We know that the angular dimension is 0.001 and the redshift is 0.5. So let's see if we can figure out how far the galaxy is and the diameter of the galaxy with this information. Let's start by trying to figure out the velocity of the galaxy. I'm starting with this approach because I can use Hubble's law. If I have the velocity, I can find how far away it is. So I want to get myself to a position where I can figure out the velocity to figure out how far the distance is. After we figure out this distance, we can do some trigonometry to figure out the diameter of the galaxy. So that's how I'm thinking about approaching it. If you remember from one of our earlier videos, the formula to find velocity, if given the redshift, is this. V over C equals z plus 1 square minus 1, z plus 1 square plus 1. Now let's plug in our value for z and solve for v. Remember, the speed of light is 10 to the power 8 meters per second. And from our calculator, we get a velocity of 1,153,84615. Okay, we want this not in meters per second, but we want it in kilometers per second. So let's convert that to kilometers per second. That gives us 1,153,804.6 kilometers per second. I rounded the values off. Now with this information, let's try to find how far away the galaxy is. We can use Hubble's law, where velocity equals the Hubble's constant times the distance. We have 1,153,804.6 as our velocity in kilometers per second. Let's plug in the Hubble's constant as 70, and now we can isolate for d. So d, which is going to come out in megaparsecs, is going to be 1648 megaparsecs. So that's our answer for how far it is. Now we have to find out the diameter of the galaxy, and we can do that with some trigonometry. Let's draw our triangle here. So we were given that the entire angle was 0.001 arc seconds. So to make a right angle triangle, I'm going to cut through here and find the radius first. So let's do that. The radius of our galaxy is at an angular diameter of 0.0005 arc seconds. We already know the distance as 1648 times 10 to the power 6 parsecs. Okay, so we have a right angle triangle here, and we have this side. We need to find this side. That means we have to use tan. So that means tan of, let's convert that 0.005 arc seconds, which is half of 0.001, because we're only taking this top half of the triangle. Let's convert that into degrees. So we're going to have 0.0005 divided by 60 to get to arc minutes, and then divide by 60 to get to degrees. This should equal r divided by, because opposite over adjacent, r divided by 1648 times 10 to the power 6 parsecs. And with our calculator, we get r as 3.99 parsecs. So this is our answer for the radius of the galaxy. So that means our diameter for the galaxy is 7.99. And that's our final answer. This is how far the galaxy is in megaparsecs, and this is how wide the galaxy is in parsecs. So to review, we went over Hubble's law, the graph that he observed. We went over some points, and the relationship between how fast a galaxy moving to how far it is a linear relationship. We went over Hubble's law, where this velocity is in kilometers per second and the distance is in megaparsecs. Then we went over the Hubble's constant and how that comes from the slope of the graph. Then we went over an example problem that actually showed up in a national competition. I'll see you in the next video. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.